Hello, multivariable kids. It has been a while, hasn't it? I miss you. I think about you. Thank you for those that I've kind of spoken to over email. This is the lesson that we would have had on that very last Friday that we just that I didn't do with all the craziness going on. I just wanted to hang out with you one last time. So this is obviously optional for you. And the two assignments on your two problems from section 4.4 for that go along with this PowerPoint. I suggest you do number 3 first, because number 2, it's the same problem. Both of them do this, the MVP method, which is what we're going to practice today. But the first one, the number 2 that you were assigned, takes a bunch of integration by parts. And number 3 is a little bit more straightforward. So let's start off with some background information that I think you're going to find helpful. So I don't know how many of you remember, or if you ever learned how to solve a system using Cramer's rules. Those of you in linear algebra probably know what this means, I think, right? Using Cramer's rule to solve a system. So this is just an algebra system, and Cramer, his rule said the solution, the XYZ solution to this system, is he proved a ratio of determinants. This is my language, so I'll tell you what each one of these means. D is for denominator and N is for numerator. So the denominator is also D for determinant, is the determinant of the coefficient matrix. And N is for the numerator. So N sub whatever is also a determinant, but is it a determinant of a manipulated matrix? And I'll show you what I mean by that. So I'm going to go over here and make my first determinant. So my first determinant is just the coefficients. Excuse me. Right, and I'm not going to do this, right? I leave it to you to practice doing this, but I got 51 when I was done with this. So that's going to be the denominator of my 3 coordinates, x, y, and z, of the solution to this system. Now I'm going to do 3 more determinants. And the 3 determinants I'm going to do, I'm going to call the first one nx, which means I'm going to manipulate the x column. So the first thing I'm going to do is copy down the y column and the z column. Then I'm going to copy down ny, which is another determinant. But this time I'm going to copy down the x column, not the y column, and the z column. And then lastly, Copy down the X column. Oops, sorry, that's a 4, isn't it? The Y column, and not the Z column. So what Kramer proved is that if you manipulate all the numerator columns by replacing them with the answer column, you'll get the numerator of the solutions. So 3. So linear algebra kids, I wonder, A, have you done this? B, have you proved this? So, and again, I'll leave these calculations to you for practice if you want, or of course you can use your calculator. You can't use it on our test, but you can use it here. I got 51 out of the first determinant. I got 153 out of the second one. And out of the last one here, I got negative 102. And because this is a math book problem, everything turns out really nicely because each one of these is, guess what, a multiple of what? You got it, 51. So now I'm going to go over here and I'm going to say my solution then to this algebraic system is 51 on top of, comma, 153 on top of, comma, and negative 102 on top of, and each one is going to be on top of 51. So what is my final answer? Boom chakalaka, thanks Kramer. I mean, it's really just as, again, I think in linear algebra you've probably done row echelon, row reduction stuff, right? But this version of Kramer's rule is something, obviously I put this in here because we're going to need to think about this of Kramer's rule in today's work. Also, the next warm-up, find the determinant, just straight up calculations, right? And remember the determinant is a number, right? That's why we got 51 and 153 and negative 102. So if you do the determinant here, again, I'm not going to do out the work, you will get 18. Now, you have a choice with the second one. The second one is a scalar times a determinant. Right? This determinant, when I did this determinant, I got 9. And what am I supposed to do with that 9? Hey, they're the same. Do you notice anything curious about the inside of this matrix and the inside of this matrix? Well, hopefully you realize firstly that the Y column, right? This column, whoops, that's still an eraser, isn't it? These columns are the same. And these columns are the same. The only column that is different is this one. That one is not equal. But what do you notice? It's kind of like, what's the good F word again? A factor. It's kind of like a 2 has been factored out of the first column. And that is a property of determinants. If you factor something out of one of the columns, the determinant, right? The determinants will be equal to that factor times the new determinant. If you take a factor out of one of the columns, take a factor out of one of the columns, this holds true. We're going to need that today. Now you might ask me, and again, maybe those of you in linear algebra have done more of this, there are more properties. Can you factor it out of 2 and then do it? I don't know. I don't remember. All I know is you need to know this property for what we're going to do today. So we are back to the MVP, right? So the method of variation of parameters, you know what we've done before, so I'm going to bounce back and forth. I've imported some of the slides into this presentation from our other variation of parameters in for second order to remind you of how we built up to what the variation of parameters was. Remember, one of the key things was we had a fundamental set of solutions. We assumed that from our complementary solution. And when we do that, when we're using the complementary solution, remember the link to the Wronskian. We said the Wronskian does not equal 0. Now, the method of undetermined coefficients doesn't always work, right? It only works if, we get the algebra to work. The MVP method will always work. And you see always is in quotes, because in order to use the MVP, you have to integrate. And sometimes you might get expressions that you can't integrate, meaning that your quote-unquote solution has integral expressions in it. That's not really ideal. You will be able to, the 2 homework problems tonight are, you're going to use the MVP method, you're going to get to the place where you need to integrate, but you're going to be able to integrate. In problem 3, it's a little nicer. In problem 2, you have to use integration by parts a couple of times. So I'm going to be referring, again, I've imported some of these slides from our PowerPoint. You can also go here and look at it yourself because I'm doing it kind of in a choppy method. But I'm trying to make, if you see the color switch, right, notice that we have a purple background here for the, and then here I went to pink because this is a slide from our old MVP lesson where I went through a proof of given a second order differential equation that is non-homogeneous, right? Non-homogeneous. We got the fundamental set of solutions, right? The complementary one, where we're assuming y and y1 and y2 are fundamental sets. Then we had the particular solution where u1 and u2 were functions, and that's what we were after. We were going to try to solve for those functions. So we differentiated the particular, and then we made a claim, and I said you need to just buy this right now. That's going to be key to what we also, to the higher order, is making this kind of a claim. And truly, and Paul, if you go through Paul's online notes on this, he does a decent job, I think, of I mean, he does a great job, but the explanation where you can read it and kind of sort of follow what he's doing is, I think, done pretty well. But it really is, I need to make these claims just to make my math easier. And then on the back end, when you're done, you're like, oh, these claims do make sense when you get to your final answer. So remember, we then differentiated the particular, and we got the second derivative, and then we subbed back into the given. And we subbed back in y double prime, y prime, and the original. And then I was like, oh, but look, what do we have here? Right? What do we have in some of these expressions up here? We had some things we could factor out and collect, and we had some nice things happen with that equation. Now I'm going to break for a second and go back to what we were, oh wait, first I want to highlight that claim. and then go to our example, which is not second order. So I want to start our example with that information kind of reminding you of what we did with second order. So this is a third order non-homogeneous, so we start with the complementary function. Now I didn't do the work of this on the slide, but this is prior knowledge and stuff that we did before, right? Where you try to look at that and see if you can factor it nicely. It's 4 terms, so can I use factor by grouping? I don't think so. So what am I going to do? I'm going to use, right, division or synthetic division and use some, yes, I'd have to do the rational root theorem, blah, 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 blah. But so far, all these examples have been nice. And when you started with something like 1 or -1, it was fairly obvious, blah, 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 blah. And yes, you got a remainder of 0, and then you were able to factor after that, right? You took a cubic, you got down to a quadratic, and you factored. So I trust you to go through that work. But what I did, I got factors of, when I was done, I got factors of that R expression, 1, 2, and 3. And that's why you see the 1x, 2x, and 3x there. So now we assume a particular solution where we use the same the same functions, right? Fundamental functions that we have here, 1, 2, and 3, but multiplied by other functions, not constants. Now, you won't have to do this for any other problem, so it's up to you whether you want to write this down or not. But this is, I'm going to kind of sort of do a proof like I did before. Only this time, notice I have to differentiate all the way to get the third derivative. But this time I'm going to use claims like this, a very similar claim. I'm going to use it a couple of times as I go through differentiating to keep the number of derivatives down, and so that I have a manageable equation. Now I'm going to go back to the pink slide and show you that what we did after we factored and collected and had things drop out of here, that's the exact thing that would happen with our third 3 derivatives and whatever. It would just be uglier and nastier. But then we got down to this system. Now look at that system. That system is our claim that was equal to 0, and this last statement here equal to the original non-homogeneous answer. Since this was just a 2x2 system, we just used substitution, and we solved for u prime, and we solved for u prime of 1, and we solved for u prime of 2. And when we did that, we ended up with this expression. We said we've got u prime 1 by itself, u prime 2 by itself, but we were after just u of 1 and u of 2, so that's where the integration came in, right? And we had to remember that we had this negative sign that came from our algebra work with solving a 2x2 system by substitution. So now I want you to remember and review these, right? Kind of look at what the denominator ended up being. We were like, oh, my Lanta. That ended up being the Wronskian, right? It was just the value of a 2x2 determinant. So now I'm going to go back to our problem. So we also, if I had done all those algebra with those same kinds of claims, just going out to using u of 3, u primes of 3, and going all the way to the third derivative, this is what I would have gotten. Notice that I have 2 claims. I have a claim with u prime and y's, and u primes and y primes. And both of those claims I needed to make equal to 0 to keep my algebra and my derivatives manageable. Number of derivatives and therefore algebra manageable. And then my third equation should look very familiar, right? It is analogous to what we did in the 2x2 system. And it was a result of all that algebra. Unlike when I did the MVP lesson for second order, I went through all that algebra, showed you how we collected like terms, canceled some stuff out, and that this is what we ended up getting. You can go through that if you want. I just didn't type it up. So this is a higher order. And if I had higher than 3, right? If I had 4th order, 5th order, whatever, it would follow the exact same format, but the last equation would always look the same, and it would also always be equal to g of t. So how do I solve a 3 by 3 system? Well, snap! I think we did a warm-up problem like this, right? I'm going to use Kramer. So what do I need to solve a 3 by 3 system with Kramer's rule? Well, you saw from the warm-up that this time I'm looking for my x, y, and z. It's kind of like this is my x, this is my y, and this is my z, right? So I kept this notation here for a little bit just to be consistent with what we'd done in the warm-up. How do we go from there to getting u's? We integrate, right? And again, I'm going to drop this notation shortly, but for right now, just to keep consistent with the warm-up, I left this nx, ny, and z, and d for denominator. So don't write all those down, but you might write the first one down, right? That d determinant is the denominator, which is the coefficient, which is the determinant of all the coefficients. So I'm going to go back for a second, right? It's all the coefficients here, right? And these coefficients come from our example. So, right, our example was all the way back. Whoa, 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 whoa. Oh, I think I freaked out my computer. No. Where the freak was our example? There it is. This one, right? So I'm using, right, my originals, right? This is in my determinant. This is the first row, right? These are the quote-unquote coefficients. So that's what you see right here. E to the x, e to the 2x, e to the 3x. Then I'm doing the next coefficients, which were the derivatives, and the next coefficients, which were the derivatives, the second derivatives, right? So we are treating these as the coefficients, right? Because we're solving for u, right? So y, third y prime of the third, y double prime of the third. That's what's in this equation. But I'm going to call this what? Oh wait, sorry. For nx, right, you're supposed to manipulate the x column. Where did those come from? Where's 0, 0, and e to the x come from? Right? Do you see that? That's right here. That's my answer matrix. I'm taking the answer matrix, 0, 0, and my function, right? Our example, our g of t was e to the x. I'm taking this column and I'm going to replace the x column first. In the next determinant, I'm going to replace the y column. And in the last determinant, I'm going to replace the z column. Right? That's Kramer's rule. That's all I'm doing. Then I'm going to make a ratio of, right, of determinants. But I want to start changing my labels. I'm going to call that determinant W. And then again, I'm going to let you do the math of this, but I'm just going to tell you what I got. when I was done with doing this, well, let me set it up once. I do want to remind you, right, because we don't have I, J, and K anymore, right? So, right, we're doing this. You have to do this top row times your mini determinants. So you're going to do e to the x negative e to the 2x and e to the 3x times a mini determinant times a mini determinant times a mini determinant, right? So again, I'll let you do that, but I got 2 e to the 6x out of this. Now, before I calculate these determinants, I'm going to use that feature, I'm going to use that property of determinants, right? Do you see what's coming? I'm going to use that property of determinants that was from number 2 of the warm-up. Out of this first determinant, I'm going to factor something out of the first column. I'm going to divide everything in the first column by e to the x. Oh, snap. And that property I showed you told you you can do that, and you'll get the same value as if you didn't do that, as long as you, good F word, factor that e to the x out front. So why this is nice is that you create a column of zeros and a 1, which makes computing derivatives of these 3 determinants nicer than the first one. So there's nothing to be done about this one. This one is a little this one's a little gross. But this one, all of these now become nicer because, didn't mean to do that. This now all becomes 0, 0, 1. 0, 0, 1. 0, 0, 1. But each one of them has an e to the x out front. Okay? So again, I'm going to write up here with this one. This was 2e to the 6x. This one was e to the 5x without this yet. And I'm leaving this off for a reason. Right? I'm leaving this off right now for a reason. Don't forget it's there, but the answer that I'm putting out here, e to the 5x, is just the determinant with the 0, 0, 1s in it. Gosh darn it. I was just trying to get to the erase one thing. So this is Wronskian 1. Which one of these is a 1 again? And each one has an e to the x out front. What I'm calling Wronskian 1 is without the multiplication or the factored out e to the x. What I'm going to call Wronskian 2 is also without the e to the x multiplied yet. What I'm going to call Wronskian 3 is without the factored e to the x. Now, if you had decided, right, you would, right, if you had made your y sub 1 e to the 2x and this e to the x and this e to the 3x or any combination of these, our labels would be different. This first Wronskian wouldn't be any different. These could be, right, in different order and maybe even a different sign every once, you know, but trust me, it'll all work out. So now what am I going to do with this? The variations of parameters formula for higher order looks like this. Can you see why I left the factored e to the x outside to match so that I would match this formula? Do you see that? So for us, right, our g of t is e to the x. That's the factored out e to the x from the determinant. Right, and it doesn't matter how many you've got. And then this is the determinant, right, with the e to the x in front. This is what we called nx. This is the determinant of ny. And this is the determinant of nz. And then what's the denominator? The denominator is, right, just our Wronskian, which was 2e to the 6x for each one of these. Crazy, huh? So let's write that out. So our u sub 1 is the integral of e to the x times e to the 5x all over e to the 6x, and there's a 2 here, right? I'm going to osmosis that out front. U sub 2 and I'm going to osmosis the 1/2 out again. Ooh, what else could I osmosis out? That -2, right? What was our nz? Oops, I'm sorry. This is e to the 3x, right? With again that 2 in the denominator osmosis out front. So this is how I'm going to get U1, U2, and U3 by integrating each one of those. So what does that look like? Simplifying U of 1, I had 1/2, right? Put those together and I got a 1, right? Maybe I should go back to where you can see these, right? Isn't this just right? This numerator is just e to the 6x, isn't it? So that's just integrating 1. And I guess I should have my dt's out there, shouldn't I? Or dx's, whatever. dx. What's this one? This one is -1, right? Because I osmosis the 2 out and a -2, so I have a -1. And then what is this? E to the x and e to the 4x, so I have e to the 5x here, and then e to the 6x in the denominator, so this is just going to be e to the -x. And then what do I have up here? And this is e to the 4x, right? Read my sloppy writing. This is e to the 4x, but it's over e to the x. So this is 1/2 integrate e to the negative 2x. And for each one of those, right, what do I get? Now I'll go to the next slide. So integrate 1 and I get 1/2 x, right? Integrate -1 e to the negative x, and I just get e to the x. Integrate (1/2) e to the negative 2x dx. I get -1/4 e to the negative 2x, right? Now I forgot what I was doing, right? I've done so much freaking math I don't remember even what I was doing. Right? I was solving not a system. The system of equations was a vehicle, right, to get me to solving a third order differential equation where we had the complementary solution. The final solution is the sum of the complementary plus the particular. And the complementary was C1 e to the x plus C2 e to the 2x and then I needed to add the particular. But remember, the particular equation, right? The particular equation started out looking like this. U of 1 times y1, u of 2 times y2, and u of 3 times y3. We found u1, u2, and u3, so we need to add that down here. But we need to fill in the u's, right? So plus u1, which is 1/2 x times e to the x, plus u2, which was e to the x times e to the 2x, plus y3, which was -1/4 e to the negative 2x times e to the 3x. Let's clean some of these up. 1/2 x e to the x plus, what is this? E to the 3x, and this is -1/4 e to the who? X, right? And then I just need to add my complementary. So y equals C1 e, oh, hey, wait a second. An e to the x, and I've got an e to the x over here, don't I? Oh, I can combine those. I don't need you. Jeez, all that work for nothing. Plus C2 e to the 2x plus C3 e to the 3x. Oh, wait, I have an e to the 3x over here. Well, that just gets combined. I don't need you either. Is this one going to go away too? Oh, no. It's an e to the x, but it's an x, right? There's an x here. So, this is it. OMG. Right? Any e to the x terms that I could put together, I did. Right? So I ended up putting what? E to the 3x and e to the x together. I should have said nx here. Oh, Malanta. That took a lot of work. Ah! And this doesn't, this should be e to the x, right? Okay, or nx. Whew, that was a lot of work. Let's do another one. Notice this time this is my g of x, or g of t in this case. I use t's this time. There's my g of t. So step one is to get the complementary. Once again, this took some division to get to, and it was -1 that I used, right, to get me a 0, and then I had a quadratic, and then I factored the quadratic, and my roots were -3, -1, and 6. And that's what you see down here. So then I assume my particular solution is functions in front of each one of my y's. Right? These are my fundamental set. y1, y2, and y3. Not y prime. And I'm not going to, find the derivatives, do my claims and whatever. We're just going to jump right to the formula. Right, so I'm going to get U1, U2, and U3. I know what goes in here. Right in here is 3 minus 4t is going to go there, there, and here. And remember, that comes from factoring out of these Wronskians so that you have a 0, 0, 1 column, right? And this is the actual Wronskian. So I just copy and pasted this one. Right, and there you see the actual Wronskian, where you have to multiply the mini determinants by e -3, e to the -3t, e to the -t, and e to the 6t. And then the first Wronskian has 0, 0, 1 in for the x, 0, 0, 1 in for the y for the second Wronskian, and the third Wronskian has 0, 0, 1. Please don't forget that that came from factoring out g of t, right, from the answer column. So each one of those Wronskians, 1, 2, and 3, has to be multiplied by 3 minus 4t, but that's what you've taken care of right here, right? That's what that is. So this integration is a little bit nastier than the first, just algebraically really, not calculus-wise. Right, so there's the first one. Right, if you combine and suck out a factor, you get 1 over 18, and then it's not bad at all. There's u sub 2. Then u sub 3. And then don't forget that those aren't your final, those results are not, still not your final particular solution, right? You need to multiply each one of these right? You're going to end up multiplying this by y sub 1, y sub 2, and y sub 3. And that's what you end up getting, right? So here you can see here's u of 1 times y sub 1, u of 2 times y sub 2, and u of 3 times y sub 3. Simplified fairly nicely, just annoyingly. And then here is the general solution, which is your particular and your complementary together. Now, if you look at that, can you see which ones, is there anything you can put together? Yeah, I do, right? I would have put, right? You don't have to write this down. I don't particularly care whether you combine them or not. Right? It just makes it for a cleaner one. Hey, oh, should I eliminate? Oh, no. As an e to the negative t, but what does it have? A t, right? All right. So there you go. That's 4.4. We only have one more lesson, which I'll also send you a video for in this unit, Unit 4. It's actually from one of the sections in Chapter 5 of your book, but Ms. P felt like it, and I agree, feels like it really fits in with this unit. So that's going to be the last one. You do have a project, right, that we handed out sometime in the few days before we went on break. If you don't have it, I'll make sure that it is on Canvas if it isn't already. So we think, again, we don't know for sure what's going on right now with grades, but we'd like you to be working on the project at some point to turn in, probably obviously just virtually by taking a picture of it and submitting it, and I'll give you more details about that. We do need to get in probably one more assessment into third quarter is what we've been asked to do. Again, this is all fluid. We're not completely sure. But we'll give you a more heads up about what that is by the end of this week. So for right now, if you can get this done, practice that homework, and maybe start working on the project. But nothing is certainly going to be due or assigned due for this week. Anything that we would ask of you to officially be turned in wouldn't be till what is today? I don't even, at least a week from today, which is when I'm recording this. It is Tuesday, I think. So the earliest we would ask something from you would be Wednesday, a week from Wednesday, right? All right. Take care. I do miss you and thinking about you and your families, and hope all is well.